Okay, thanks everyone for coming. So I'm going to talk a little bit about some fundamental formulas from metrical algebraic geometry and how they connect to some classical formulas from, well, antiquity up to modern times. So I'm interested in metrical algebraic geometry here today. So geometry looked at algebraically and with a metrical approach. So we're interested in making measurements in this setting of algebraic geometry. And for our purposes, we're going to think of the subject as being divided into two halves, the affine and the projective views of algebraic geometry. So the affine view, the main objects, affine n-dimensional space, where we have points of the form x1, x2, up to xn. So those are our basic points. And for example, A2, the usual plane with some point 2, 1 perhaps, another point 4, 3, and so on. Of course, we can also consider other things. We can consider lines. We can consider conics. Consider cubics. In higher dimensions, we can think about surfaces and more general aspects. Closely related to this is the idea of a vector space. So there's an associated vector space which is perhaps more familiar to the modern student. So associated to 2 points, we have a vector. So A and B are 2 points in our affine space. Then we have a vector V, which is the vector AB. And that vector, the vectors form a vector space. So associated to this is what we might call Vn. And maybe in this case, for example, this vector would be the vector 2, 2. And I'll write the vectors in round brackets to distinguish them from the points, which are in square brackets. So the vector space consisting of things of the form x1 up to xn. And this has the familiar algebraic properties of being able to add and scalar multiply. Okay, over in the projective side of things, so this is the other sort of side of the coin of algebraic geometry, we have projective space, and Pn consists of things of the form, say, x1 to x2 to xn to xn plus 1. So this is a proportion now. And the meaning that if we multiply by a non-zero scalar everything, then it fundamentally doesn't change. And so, for example, if we're thinking about the projective line, P1, then we can think about that as consisting of things like 2 to 1, which is not just a point, but actually a line, representing a line through the origin in two-dimensional affine space. So the projective space can be thought of as one-dimensional subspaces of the corresponding affine space. So that's 2, 1, and maybe 4, 3 would be this one here, 4 to 3. Of course, the point 2, 1 in our space would be on that line, but it's actually the line itself, which are the objects of the projective space. So we want to look at these things from a metrical point of view. That means we want to make measurements in the spirit of classical geometry, but we want to do so in an algebraic fashion. So the key ingredient that we need to add to our geometry to get metrical structure is a quadratic form. So the quadratic form is more naturally associated here to this affine situation, or actually more particularly to the vector space. If we have a vector v and we have a vector w, we have v dot w, which is a symmetric bilinear form. And that's really the starting point to a metrical structure. There's also the corresponding metrical structure over here. So we can also think about having two vectors that represent these lines, say the vector v and the vector u. Then over here, we can define a metrical structure, but it's a little bit different. So let me introduce notions of quadrants. Maybe I'll start on this side. So I want to get this all on one board. So maybe I'll write up here. So that the quadrants of a vector v is v dot v. So that's the main metrical measurement that we get, the quadratic form associated to a symmetric bilinear form. And over here, the corresponding projective object is going to be a projective quadrants. So let's say these are two points A and B in our projective space. So let's define the quadrants between A and B to be a 1 minus u dot v all squared over u dot u times v dot v. Okay, so this is how we're going to introduce metrical structure in the projective setting. We'll call this projective quadrants. And over here, to get a metrical structure, I'm going to define, maybe over here, the quadrants between the point A and the point B will be, by definition, the quadrants of the vector AB. Okay, so the starting point in both situations is a symmetric bilinear form on an affine space or a vector space. And from that, we can build a notion of quadrants where we're measuring either the separation of points or the sizes of vectors. Or in the projective setting, we have notion of projective quadrants between projective points.
Do you care if your projective, your symmetric bilinear form is degenerate?
Yes, that's a good point. We can think about degenerate forms, but we prefer that things are non-degenerate. So non-degenerate, let's assume for now that everything's non-degenerate. So that means that if you associate a symmetric matrix that represents this bilinear form, that its determinant is non-zero. Thanks for that. It just makes life a lot easier. Okay, so what we're interested in doing is trying to establish what are some of the fundamental formulas in this subject, just at this level, where we're working with these two notions. And I'm going to talk mostly today about the affine situation. At the end, I'll probably have some time to mention that there's analogs of what I'm going to talk about in the projective setting, and that's quite interesting. But we'll see that there's already quite a lot to be said in this affine setting. So let's turn to the affine one-dimensional case. It's perhaps a little bit unusual to start with one dimensions, but I like to start at the beginning of things and to do things completely completely in a way.
So when you guys said this, I may have missed it, but are you assuming that thinking about the real numbers only, or they come in an arbitrary field? Or?
Okay, so I didn't say what our number system is. So I'm a disbeliever in so-called real numbers. But let's say that what we prefer to do is to work over a general field. So I'm interested in a theory which is as general as possible, so that the actual underlying field is not really necessarily known. And in fact, also I'm prepared to work with more general bilinear forms than the usual Euclidean one that maybe we're mostly familiar with. So I want a theory that works for example, relativistic quadratic forms, or maybe like a trace form that comes up in operator algebras, or killing form that comes up in Lie theory, so that we're able to do this kind of geometry in a rather general setting over a general field, including over finite fields. Okay, so we're going to start with the affine one-dimensional case, which is deceptively simple. All right, so the affine one-dimensional case, we're just talking about a line. I'll draw it like sort of a rational number line. And we have points. There's a point A. There's a point B. There's only one coordinate. The quadrants between these two things is very simple. We have to choose a symmetric bilinear form. So up the scale, there's only one. So we might as well just define the quadrants to be the difference b minus a squared. Okay. So the square ensures that things are symmetric. We're not taking any absolute values because we want to stay completely in the algebraic setup. We don't want to do any square roots or any infinite processes. Okay, so this is the basic definition. And then what can we say? Well, it turns out that we can say a lot of interesting things. And the starting point is what happens when we have 3 points. So we'll have 1 point. Maybe I won't specify what the points are. I'm more interested in what the quadrances between them are. So let's say that the quadrants between those 2 points is A, and I'll denote quadrants with a little rectangle. The quadrants between these 2 points is B, and the quadrants between these 2 points is C. So now we come to probably the fundamental formula of the subject, even though it's very simple, which is the triple quad formula. Which tells us what the relationship is between these 3 numbers, A, B, and C. And the formula is that A plus B plus C squared equals 2 times A squared plus B squared plus C squared. All right, that formula deserves to have some red around it, so let's put some red around it. Okay, there's an alternate, well, actually, there are several alternate ways of writing it. We could also write it as, equivalently, as 4AB equals A plus B minus C all squared. That's just a rewriting of the same relation. So let's do an example. Suppose that our points were say 0, 1, and 5. Those are our points. Then the quadrances are 1, 16, and 25. And so the claim is that these numbers satisfy the relation that 1 plus 16 plus 25 squared equals 2 times 1 squared plus 16 squared plus 25 squared. It's a little bit easier if we check that one. If we say, write 4, say, times 1 times 16 equals 1 plus 16 minus 25 squared, then that's 17 minus 25, that's 8 squared, 64, and that's 64. So we can check that form of it. Okay, I'm going to introduce a function here. So let's introduce this script A function defined by just the difference between the left and the right-hand sides. A plus B plus C squared minus 2A squared plus B squared plus C squared. I'm going to call this Archimedes function for reasons which will become clear a little bit later. So there's Archimedes function. And we'll say that 3 numbers, A, B, and C, form a quad triple precisely when this Archimedes function evaluated on them is 0. Okay, so let's first of all see why the triple quad formula is true. So it follows, one way of seeing it is that it follows from the following fact, that if we have 3 numbers, such say that A plus B equals C, and in fact, let me be a little bit more general. Let's say that A plus or minus B equals plus or minus C. If I have a linear relationship between 3 things, and I introduce the squares of those 3 things, so capital A is A squared, capital B is B squared, and capital C is C squared, then A, B, C is a quad triple. In other words, it satisfies Archimedes function or the triple quad formula. And so let's just verify that. So if we take this thing here and we square it, we square A plus or minus B squared plus or equals plus or minus C. We square that, then we get capital A plus or minus 2 little a b plus b equals capital C. And then if I bring everything to the one side, I can write that as a plus b minus c equals plus or minus 2ab. And then if I square that once more, I get a plus b minus c squared equals 4ab. And that is, we've said, a version of the triple quad formula. So this is an important fact, that whenever you have a linear relationship between three things, then the squares of those three things satisfy the triple quad formula. So this is a very general fact which is useful in a lot of different situations. And let me connect it to some classical investigations of Bezout and Euler, and also a topic that Newton was interested in. So the 17th and 18th century mathematicians were interested in solving equations, but not just linear equations. So for example, suppose that you have two quadratic equations, x minus p1 equals q1, and x minus p2 squared equals q2. So x minus p1 squared equals q1, and x minus p2 squared equals q2. So we have two quadratic equations, and we'd like to say, what does that imply about the coefficients? Well, so it turns out that if these two equations have a common solution, then we have that q1, q2, and p1 minus p2 squared form a quad triple. Okay? This is an equation that the 18th century mathematicians referred to as a resultant. This is the result of eliminating x from this system of equations. In fact, if you take these two equations and you just take the difference between those two equations, you can easily solve for x. You get x equals p1 plus p2 over 2 minus q1 minus q2 over 2p1 minus p2. And then the usual thing would be if to establish a relationship between the coefficients, then if we plug that back into either one of the equations, then we get an equation only involving the four original coefficients, and that turns out to be essentially this one here. But we can geometrically see that this is going to be so by looking at the geometry of things. So here is the point P1 on our axis, and here is point P2, and here's our point X. We're assuming that X satisfies the two quadratic equations. So that means that the quadrants between P1 and X is Q1. That's exactly what that's saying. And that the quadrants between P2 and X is exactly Q2. That's what that's saying. And the quadrants between P1 and P2 is going to be P1 minus P2 squared. And so we see from the geometry immediately that these three numbers satisfy the triple quad formula, which is that relation there. I can't help but also, just for your own interest, give you the following alternate form of this. This would have been well known to Euler, etc. So a1x squared plus b1x plus c1 equals 0. If we rewrite the quadratic equations in this alternate form with these kinds of coefficients, then the corresponding identity becomes this determinantal identity, a1, c1, a2, c2, all squared equals a1, b1, a2, b2, and b1, c1, b2, c2. That's just a rewriting of the resultant formula. All right, so now let's make things a little bit more exciting by making things a little bit bigger. So now I'm going to look at 4 points on the one-dimensional situation. And so I'm going to have quadrants as, let's say, A here. From here to here it's A. And maybe from here to here will be B. And from here to here will be C. And from here to here will be D. Okay, these are all quadrants. Okay, so we have 4 points. We're going cyclically. From here to here is A, from here to here is B, from here to here is C, and from here to here is D. And we're interested in what's the relationship between these 4 quadrances? Well, let me introduce the 2 other quadrances which are floating around, which are this one here, from here to here, A, B, I think I should call that one R, and the other one from here to here, let's call that P. Okay, we want to know what's the relationship between A, B, C, and D. We're going to use these 2 auxiliary ones, R and P. So we'll note first that A, B, and P is a quad triple, because that point, and that point, and that point are a triple. And we also know that C, D, and P is also a quad triple, because from here to here, from here to here, and then back there, it's also a quad triple. So here we have 2 quadratic equations. So I'm going to write out these quadratic equations. The first one is 4ab equals a plus b minus p squared, and the next one is 4cd equals c plus d minus p squared. So those are 2 quadratic equations which have a common solution p. So from what we just did, we can write down a relationship between the 4 other quantities floating around. In fact, the relation is exactly that the Archimedes function applied to the right-hand side, which is in this case the left-hand side, 4ab, 4cd, along with the difference a plus b minus c minus d squared, that's going to be 0. And we can write that in a more symmetrical form in the following way, that it's a plus b plus c plus d squared minus 2 times a squared plus b squared plus c squared plus d squared, bracket, and all of that squared equals 64abcd. And we'll put that in red. So that's a relationship between the 4 quadrances A, B, C, D that you get by looking at 4 points in this one-dimensional setting. There's a few other things that we can deduce. Because we have 2 quadratic equations, we can not only tell us what the condition is, but we can actually solve for P is without using the quadratic formula. That's the common solution, so we can take the difference between these 2 equations, solve for P, and we get P equals a minus b squared minus c minus d squared over 2 times a plus b minus c minus d. And then we play the same game with R and its relation. So we get a similar formula for R as a minus d squared minus b minus c squared over 2a plus d minus b minus c. So I point out that, okay, we're talking about quadrances here, not distances, so there's no distances at all. But that means that the position or the relative positions of points is irrelevant. Okay? So if you're talking about distances, you always have to have a diagram to tell you which things you're going to add up and which ones you're going to subtract. So these are symmetric formulas, so they apply no matter where the points are located. Okay, so there's a few now kind of remarkable consequences here. So one of them is that for PR, if you take this expression and take that expression and you stare at it, or preferably apply your computer to it, you can see that you get a minus b plus c minus d all squared. So a bit of magic at this stage allows us to take the product of these 2 expressions and simplify. Just simplify using sums of squares and differences of squares and so on, and to get that formula there. And similarly, we get formulas for the other two. So we have 4ac equals b minus p plus d minus r all squared, as well as 4bd equals a minus r plus c minus p all squared. And then we get another remarkable sort of bit of magic when we look at these three expressions, and we find that a of ac, bd, and pr equals 0. In other words, these, well, after we move the 4, the product PR, the product AC, the product BD is itself, that set is another quadruple. And that's an identity just involving these three expressions. So if you just take the Archimedes function and you plug in this thing, and this thing, then identically you get 0. So let's introduce just a bit of terminology. So we had a special function for the 3 case. Let's introduce the quadruple quad function. So Q of A, B, C, D will be A plus B plus C plus D all squared minus 2 times A squared plus B squared plus C squared plus D squared all squared minus 64, the product A, B, C, D. And while I'm at it, I'm also going to define D of A, B, C, D, sort of a curly D, which will just be the first thing here. A plus B plus C plus D squared minus 2A squared plus B squared plus C squared plus D squared. So this will be called the quadruple quad function. Quadruple quad function. And this will be called Descartes' function. Why Descartes' function? Because Descartes was considering the problem of Apollonius, which is talking about when you can position a fourth circle tangent to 3 others. In the special case, when you have 4 mutually tangent circles. And he said, okay, let's look at these radii. So the radii R1, R2, R3, and R4. And if we define the curvature, Ki, to be 1 over Ri, that's the curvature of the circle in the usual sense of differential geometry, then he discovered that D of K1, K2, K3, K4 equals 0. That was famously rediscovered by a famous chemist, Nobel Prize-winning chemist Soddy in the earlier part of the 19th century, who wrote a famous verse celebrating this idea called the Kiss Precise, which you might like to look up. It's a pleasant little verse that puts this mathematical formula into verse form. Okay, so that's been a little bit of an introduction. And now I want to change gears and go back to antiquity. And now we're going to have a look at some classical results from geometry, some of the most famous results, in fact, in all of the history of mathematics. And we're going to see that they're intimately connected with these 2 formulas that I've shown you today so far. But it's not obvious that they are. Okay, so let's go back in time to 60 AD, to Heron of Alexandria, who came up with the following formula for the area of a triangle. So you have a triangle with side lengths A, B, C. Okay, side lengths now, not quadrances. And he discovered that the area was the square root of S times S minus A times S minus B times S minus C, where S is the semi-perimeter, half of A plus B plus C. Arab sources, in fact, though, suggest strongly that Archimedes knew this almost 200 years before Heron. So it's no doubt known to Archimedes, but we don't actually have tangible proof of that, at least not direct proof. So this is a lovely formula for the area of a triangle. It used to be taught to all high school students. Sadly, no longer the case, unfortunately. Okay, now we move forward to maybe 500 AD to Indian mathematician Brahmagupta, who investigated a similar kind of situation where we have a cyclic quadrilateral with side lengths A, B, C, and D. And Brahmagupta's formula is that the area is equal to the square root of S minus A times S minus B times S minus C times S minus D, where S is, again, the perimeter divided by 2. This is a generalization of Heron's formula. It wasn't the first result, though. We should also draw the diagonals and look at their lengths, which we'll call little p and little q, like that. So there's another famous formula of antiquity that goes by Ptolemy's theorem. So Ptolemy, about 150 AD, who also, in terms of the cyclic quadrilateral, showed that P times, oh, sorry, let me not use Q, but rather R, because Q has more meanings. So let's use R. Yes, P, R. P times R equals A times C plus B times D. So the product of the diagonals is the sum of the product of these opposite sides plus these opposite sides. All right, so these are the most famous formulas for cyclic quadrilateral. But Brahmagupta, in fact, also discovered more things. So Brahmagupta also discovered that P squared is equal to AC plus BD times AD plus BC all over AB plus CD, and that R squared equals AC plus BD times AB plus CD over AD plus BC. In fact, the situation is a little bit more than this. It turns out that there is actually two other pictures that one should draw with the same circle. So if we take those same four side lengths and rearrange them a little bit, so A will keep where it is, and let's say we switch B and C around, so that now there's C and there's B, and D is still there. No, probably not a very good diagram, but that's the idea. And over here, we'll do the same kind of thing, but we'll switch C and D around, so that there's C now, and then there's D over here, and then there's B over here. Then we get three other quadrilaterals which have the same area as the original one. What we've just done is we've moved, if there's a center of the circle, we've moved the slices of the pie, rearranged the slices of the pie, making up the quadrilateral. So they have the same areas. But the diagonals are a little bit different. So here there's a BC here, so that's still going to be R. But there's now going to be a new diagonal that we didn't see before. Let's call it O. And that new one will also be over there, O, along with the other example of P. So there's, in fact, another formula that we need to add, which is that O squared equals AB plus CD times AD plus BC over AC plus BD, which sort of completes the threefold symmetry of these formulas. Okay, so very classical results. And then at some point, and I'm not quite sure when this happened, but at some point people realized that this actually only works for convex quadrilateral. You could also consider the situation of a non-convex quadrilateral. So for example, something like there's A, there's B, there's C, there's D. What is the area of this non-convex quadrilateral? Well, it turns out that there's also a similar formula. The area equals square root of S times S minus A minus B times S minus A minus C times S minus A minus D. Right? That's a Brahmagupta type formula for a non-convex cyclic quadrilateral. Non-convex cyclic quadrilateral. And there's sort of similar kinds of formulas that you could write down for the diagonals in this case, but there would be, instead of having terms like AC plus BD, we'd have terms like AC minus BD throughout. Okay, so these are all lovely formulas, but from my point of view, they're not entirely satisfactory because they don't fall into the realm of algebraic geometry. I would like them to sit inside of algebraic geometry. So they don't sit inside algebraic geometry for a couple of reasons. The main one is that the notion of length is not an algebraic geometrical notion. It involves a square root, which is taking you outside properly the four basic operations of algebra. And also there's this sort of sensitivity towards convex and non-convex, which is a little bit hard to frame entirely algebraically. If we, for example, ask, well, what kind of analogs to finite fields or to relativistic geometries can we look in these directions, then we have perhaps some problems finding the corresponding formulas. But it turns out that there are analogs of these things that work for finite fields, and there are analogs that work for relativistic geometries and more. But we have to look at these from a different point of view. Basically, we have to take the two formulas that I started the lecture with and apply them. Okay, so it turns out that the triple quad formula and the quadruple quad formula are just the algebraic machinery that we need to understand these formulas in a more general, all-embracing kind of way. And so why is that? Well, it comes, one way of establishing this is to have a look at our triple quad function, what we call an Archimedes function, and replace the capital A, capital B, capital C that we used in the definition with little a squared, little b squared, little c squared. What we do is we find that this thing factors as a plus b plus c times minus a plus b plus c times a minus b plus c times a plus b minus c. Okay, and then we see that that's actually 16 times s minus a times s minus b times s minus c, where s is a plus b plus c over 2. And so we see that this is, from Heron's formula, this is 16 times the square of the area. So now it's giving us an alternate form for the area of a triangle whose quadrances are capital A, capital B, capital C. We now see that we can introduce, say, A, which is by definition 16 times the area squared, which is just, well, it equals A of A, B, C. So that same function that determined the relationship between three collinear points in the one-dimensional situation, that same quantity, when we go to the two-dimensional situation, measures the size of a triangle. So that one-dimensional situation is somehow seeing the higher dimensions. And in fact, giving us a much nicer formula, so I call this Archimedes' theorem in honor of Archimedes, who would not have been surprised by it, I'm sure. Who knows, maybe he even formulated it that way. Okay. This is an algebraic formulation. So if you have a triangle in the plane and you want to calculate its area, and you know the three side lengths, forget about the lengths, work with the quadrances instead, and just apply this triple quad function. What you get is 16 times the square of the area. And no irrationalities are needed. In particular, if you extend the notion of area to finite fields or any other field, then the formula still makes sense. How about to the situation of the cyclic quadrilateral? Well, now let's consider quadrilateral with quadrants is capital A, capital B, capital C, capital D. And the diagonal quadrants will be P and R, just all capitals now. Then Ptolemy's theorem is now restatable. Okay? Instead of having a linear relationship between the product AC, the product BD, and the product PR, between those products of lengths, we're going to have a quadratic relationship between their squares. Ptolemy's theorem is that A of PR AC BD equals 0. We started by saying that if we had a linear relationship between three things, then the squares satisfied a quadratic equation, and that was the the A function. And so we can restate Ptolemy's theorem this way. And when we do that, we see exactly the same result that I wrote down earlier. That was a result that we had already established for the 4 points in the one-dimensional situation. So we see that Ptolemy's theorem itself is just a two-dimensional blow-up in some sense of this relation which is just holding linearly in one dimension. And what about Brahmagupta? Well, to get Brahmagupta, we look at the quadruple quad formula, which I still have up there on the board there, that sort of big fourth degree thing, and look at Q evaluated at A squared plus B squared, C squared, D squared. So that turns out to factor as minus A plus B plus C plus D times A minus B plus C plus D times A plus B minus C plus D times A plus B plus C minus D. Okay, that's the first half. And then the other half is A plus B plus C plus D times minus A minus B plus C plus D. Minus A plus B minus C plus D, and minus A plus B plus C minus D. And what's that telling us? Well, if we look at that thing, that turns out to be, by both Brahmagupta's formula in the traditional convex sense and also the non-convex analog of the Brahmagupta, both are contained in here. The first 4 factors are classical Brahmagupta's formula. The last 4 factors are exactly the replacement in the non-convex situation. What we're getting is the product of the quadrias of the 2 quadrilaterals, cyclic quadrilaterals that we can create from 4 quadrances. So when I say quadria here, I'm using the definition that quadria always means 16 times the square of the area. So if you look at the literature, you will see this expression comes up over and over again in this subject. It somehow has some special role. Okay, so I can now give you a modern version of Brahmagupta's formula. The cyclic quadrilateral quadria theorem. Quadria refers to this quantity A, which is 16 times the square of the area. Okay, and it's that if a cyclic quadrilateral has quadrances A, B, C, D, and A equals 16 times the area squared, then the relationship between the square of the area and these 4 quadrances is given by a quadratic equation. A squared minus 2dA plus Q equals 0, where Q is Q of A, B, C, D, our quadruple quad function, and D is D of A, B, C, D, our Descartes function. So this last part here is not a surprise if you believe what I've said over here. I've said that the product of the 2 quadrances turns out to be these things. So here you're seeing the product of the 2 quadrias, and It's an additional statement about the sum of the two quadrias being given by Descartes' formula. So this is a formulation of Brahmagupta's result, which A, works for a general field. As long as you throw in the appropriate determinant factor, it will work for a general quadratic form, so it has a relativistic analog. It makes sense relativistically. We can talk about cyclic quadrilaterals with sort of rectangular hyperbolas. And moreover, it's amenable to a purely algebraic proof. So what we do is you take your circle, whatever it is, and you rationally reparameterize it. Here's my favorite parameterization. There's a parameterization of the unit circle. Okay. Once you have your circle parameterized, then this just becomes an elaborate identity, some huge identity that you just compute, and you get your computer to check that after all the smoke clears, you get 0 on the right-hand side. So we could circumvent any kind of classical geometry or constructions or anything else. It's just purely algebraic, which means that it works in much greater generality. Okay, so I have just a few more minutes, so I'd like to just say a little bit about, just mention the fact that the problem of what happens for the cyclic pentagon was unsolved for about 1,400 years. Okay, naturally, people asked, what's the area of a cyclic pentagon in terms of the sides? And it was only due to the work of David Robbins in 1995, I think, that the formula for the area of a cyclic pentagon in terms of its 5 side lengths was written down. And it turned out to be a 7-degree equation. 7-degree equation in basically this quadria. But it turns out that, in fact, Mobius knew this. Mobius had also thought about this question and had realized that there was a 7-degree relation that the quadria had to satisfy, but he wasn't able to write it down what it was. But Robbins, I don't think he was actually aware of Mobius's work, but in any case, he'd been thinking about this problem for many, many years, and eventually, since he was a teenager, and eventually he cracked this and wrote down this beautiful 7-degree equation. And when you write down that 7-degree equation, eventually you get some constant term. There's some constant term. The constant term, which is, of course, the product of the 7 different possibilities. If you're given the 5 quadrants, you can build a lot of different ones. The product here turns out to be essentially the, not quite, but almost the quintuple quad function. The thing that you get when you examine what's the relationship between 5 points on a line. The 5 quadrants is formed there. It turns out that there is a formula. Maybe I'll just finish by writing down what that formula is. So I'm going to not write it down in terms of A, B, C, and D, but rather in terms of the symmetric functions. So there's some elementary symmetric functions that you want to work with when you're doing bigger things. So here's this quintuple quad formula. It's 2048 times E1 cubed minus 4E1 E2 plus 8E3 E5 minus 64E4 minus 4E2 minus E1 squared, all squared. Okay, that's that relation there. If I call that, say, T, then it turns out that what's in Robbins' formula is T times that factor E1 cubed minus 4E1 E2 plus 8E3. And in fact, you can sort of see inside here, if you look carefully, you'll see the triple quad formula right there. And if you look a little bit bigger, you'll see the quadruple quad formula there. And it certainly suggests that there's, in fact, this infinite hierarchy of formulas that you get by, you keep on extending this if you know how, to get formulas that give you more and more information about more and more points along a line in the one-dimensional situation. And I don't know how to write those down. I mean, in a sort of abstract sense, I know how to write down, but as an element, as a polynomial in the elementary functions, I don't know how to write them down in general. That seems sort of intriguing that this thing goes on. Okay, so this is all the affine story. Perhaps later in the year I'll give you the projective story. So it turns out that everything that I've said here, or almost everything, has a projective version, which is one ups the ante. Things get more complicated, but also in some sense richer as well. So I might talk to you about that some other time. Thanks.